Okay, so next step will be a second coordinate system. And as you can see, the original system is kind of off from the force direction. Okay, so if we press F8 and we want a axle at this force, the direction of the force, and the origin of this coordinate system will be in the middle plane of this handle and those pins. So next we how we insert, we go to insert model preparation and coordinate system. Okay, now so we know we want to have a z direction which is the same as the old one, and we need a new axis, then a different origin. So we will pick this option. Okay, then first we will define the origin point. So let's turn off the 3D and 2D mesh, and then two place you can put the any place actually, um, but preferably I want to put this in the middle of this pin. So we'll put between these two spiders, or you can put uh, between this two force, the two nodes where we apply force. And if we put here, you can measure the distance from the point of applied force to this the pin. So you got right away you got the distance of this between these 2 points, and you got another distance from the pin, this pin to this pin. Also, you can measure the angle of this vector with respect to the new axis. So it's hard to visualize by just talking. So go ahead and specify this point. We will need open the point dialog. Then we will choose between points. Okay, so we'll pick this one and the bottom of this spider. So we'll be between two spiders. And next will be the z direction, which is exactly the same as the old one. So we'll pick z. And x is the vector that's pointing, or that's the same as the force vector. So we'll pick this center node, okay, where the force applied, and from that point to center of this spider. That'll be the direction of our load. Then it should be okay. Click. So this is our new system, and as you can see, we have ZC here, which means current coordinate system. If you want, we can right click here and set as working coordinate system, or we don't really need this now. We'll be using this in the sim. So next, we are down here in the fan. So we change the material, put a new coordinate system, and in the same we did modify the constraint and modify the force. So I think here we are good to go for the simulation. Let's go back to the sim first, and if you want we can do a save all. Okay, now for get the force in the bushings, okay, we will create a group, and you can do that in the fly in this solve attributes. Okay, so again we go to case control and output request. So here we need to enable the force and put that in print. So which entity we want? We want all the bushings. So now here we don't have anything here. We have option you can do all or group. And now So we need a new group here, okay, which we don't have any. The group is here, okay, in this folder. So you can add a new group here. It's the same as you right click here and add a new group. So anyway, then you will get this dialog box. Then how do we pick those bushings? You can expand your fam in the same here. Then you can expand your 1D collectors, expand all the CBush collector. So in my case, I have 3 collectors. You might only have 2 or only 1. So in this case, we have 5 CBush here. In the model Data demonstrated has 7. So we can pick. You don't need to press shift, just click. Okay, click 1, 2, 3, 5. So you got 5 CBush. If you accidentally selected others, it's fine. I think in the Apple 6 it will only show you the bush, the force on bush. So okay. Anyway, so you should be careful when you come back here. It will not select the group you just created. So you need to drop this again and pick this group, and it will show you here as well as on the screen. Okay, and okay, and that will be done for the. Let's go back, have a look at the SPC force. Print. Okay. So this will be a whole process of modify the model from lab 9, and we are good to go. And if you click solve, you will get the final results, and hopefully that will be the same as what we saw in on Wednesday's class. Okay. So now it's down, and that's a good sign. Okay, and movie here. Okay, so we can also go to the folder, open Apple 6, and this one is mine, what we just did here. Okay, I got 5 CBush, and you got SPC force on top. Then if you want to compare, that's the value from, I don't know how to make them 2 windows. Anyway, so you can see, as you can see, he had extra 2 CBush. We have the top 5 here, okay, 6.11, and that's exactly pretty much the same on the bushings. Then you got the SPC force. It should be very small. Okay, so e to the minus 5, and you got 0 on the. That's a constraint on the handle. So it only has something on the z, which is very small also. So that's telling you that this setup is okay. You got SPC force close to 0 because the setup is self-equilibriant. All right, and now let's demonstrate what will happen if we don't have the constraint here. And if you know what will happen, you can stop right now. And this is what Dr. Zada did in the class. Okay, and it's just for telling you that we need this constraint. If it's not there, this cutter will rotate like this on with respect to the wood, and that will be your rotating axis. Okay, so let's kill this first. Oh, we can just, I think you can deactivate. Oh, make sure this, just move this. Okay, remove this one, and absolutely this will not run. Oh, well, there will be no results. Alright. Okay, that's because this thing is rotating and the matrix is not convergent. So we will need to modify the attributes. Okay, and in here we'll go to parameter instead of case control, and we can click here parameters, and that'll be B bailout. Okay, so that's the parameter we're looking for. Bailout means 0 means if there's something wrong, you got NX will quit or Nastran will quit. So if you put bailout to -1, that means no matter how big the matrix go, it will keep calculating until you get the results. So let's put this bailout to -1 and click OK, and now we can calculate. And so you can see it's not correct, but it will give you a direction of what will be if there's no constraint on this point. Still no results. Okay, let's go to the Doc-Zadus model then. Okay, so basically, if you don't have this, okay, I changed that. Anyway, if you don't have that constraint, you will have displacement, z direction, that will be 38 on z direction. So this whole thing, the handle will go up 38 inch, and which is basically rotating on this piece of wood. And that's what he did in the class, telling you that for this model, beside this fully constrained, you still need to kill the z rotation, z direction to kill this rotation of this whole structure. Okay, so anyway, this will be the correct answer. So that's your reference. Okay, and that's it. Thank you very much.